Hello, this is the third part of impulse and momentum. In the last video, I showed you how momentum can be used to rewrite Newton's second law, which says the net force is equal to mass times acceleration. Now we know that the right-hand side can be written as delta P over delta T. Now, this will be the net force on the object, and this will be the change in the momentum over some time, delta T. Now, how about checking Newton's third law to see how momentum applies to that? Let's remember the third law, Newton's third law. Let's think about two objects, A and B, interacting somehow and exerting forces on each other. So let FA be the force B exerts on A, and FBA is the force A exerts on B. Well, these could be two balls hitting each other, or they don't even have to touch each other. These could be two planets interacting gravitationally. Okay, it doesn't matter what form of interaction this is. Newton's third law says that these will be equal in magnitude, but opposite in direction, which means this, all right? But they will be equal in magnitude. So FAB has the same magnitude as FB A. Now let's take this and then write these forces in terms of the change in the momentum of these objects, okay? Assuming that FAB, for instance, is the only force acting on A, this means delta PA divided by delta T will be equal to, on the right-hand side, negative delta PB over delta T. And we can rewrite this as delta PA, if we move this term to the left-hand side, plus PB will be 0. In other words, if I define a total momentum, which is the sum of momentum of A and the momentum of B, this will not change before and after the interaction over some time. So it will be conserved. The total momentum is conserved. So I can write it as P total before will be equal to P total after. Here I made the assumption that FAB was the only force, therefore the net force acting on the object, then the momentum, total momentum, is conserved. But if there are external forces present, of course the momentum will not be a conserved quantity, okay? But for collisions, this will be good enough to work with, right? This principle of conservation of momentum. The thing you should always remember is, though, this is a vector quantity, a vector equation. So it has to be satisfied with all components in all directions. Okay, so imagine two billiard balls colliding, okay? And assume that they don't have the same mass. This will mean ma, the mass of the first object, times its velocity before, one means before, right? Plus the second object, its mass, times its velocity before the collision. Okay, this is the total momentum before, will be equal to the total momentum after the collision or interaction. MB, VB, 2. All right, so this will be the starting point when we analyze collisions. Okay, so this equation here is a consequence of Newton's second and third laws. As you saw, you know, I mean, instead of this, you could start with the calculus version, you know, so dpa by dt would be equal to negative dpb by dt. But if you haven't seen calculus, it's okay. Just keep in mind the same thing. So let's box this. This is our fundamental conservation law when we solve problems that have to do with collisions of objects. All right. Now what we need to do now is a classification. We have to classify the collisions based on two things. The first will be a classification based on geometry. The second, what happens to kinetic energy. So collisions, let's separate this to two types of classification, let's say. And number one, based on, let's say, geometry of the collision, and then what happens to the kinetic energy. All right, so what do I mean by geometry here? Let's say we have just two objects, A and B, like two billiard balls, and they are on a collision course, approaching each other. Or one could be stationary, the other one is approaching. Doesn't matter, depends on what reference frame you're using. If this happens along a straight line, okay, such as this, and I'm going to put the first ball right here, and the second ball right over there. Okay, so that the centers of those balls are perfectly lined up with the line. And let's say these are the velocities. Velocities before. What you expect is, again, a movement along the same line after the collision. I mean, they can bump like this and move in opposite directions, or they could end up moving in the same direction, you know, depending on the velocities and masses, of course. But before and after velocities are lined up along the same line. So I draw the after picture here. These balls are moving in the, let's say, opposite direction. It's just a one-dimensional problem. Everything happens along the x-axis. Now that's one type of collision, which we will name a head-on collision. Head-on collision. As opposed to a glancing collision, which is more like the example I showed you in the previous video. That happens when these are not lined up to begin with. So let's try to draw it again. So here's the line that represents the path of the ball on the left. Okay, let me use a different color for the velocity vector. This is the direction it's moving, right? But the second ball, you know, is not centered. It's offset like this. And assume it's either stationary or moving to the left. All right. Now you may say in the before picture, you know, it's only motion in the x direction. Yes, but what happens once they collide? So the first ball will most likely move in this direction here, and the second one will end up moving maybe in this direction. Okay, and these all depend on the masses and the initial velocities and all that, but now it's a two-dimensional problem. All right, and this type of collision is called a glancing collision. A glancing collision. All right, so this is based on the geometry, just two types for now. Head-on versus glancing. Head-on is a one-dimensional problem. This is 1D. A glancing is 2D. So there's X and Y, okay? So if I want to take my momentum conservation equation and apply it to a head-on collision, all I need to do is pretty much to drop these arrows, and if the velocities are to the right, they're positive. If they're to the left, they're negative. That's it. But for the glancing collision, this is a compact form. It really means two equations, one along the x direction and one along the y direction. Keep in mind that there will be two equations to work with in the 2D problem. And that's based on geometry only. Now, there's another way to classify collisions, and that's based on considering what happens to the total kinetic energy. All right? It'll be the total kinetic energy, not just the kinetic energy of A or B. Let's rename these A or MA and MB. These are the velocities before VA1, VB1, and this is VB2 and VA2, right? You can name them similarly. But what we need to check, what happens to the kinetic energy total. So kinetic energy total, let's say before. For this case, for instance, that'll be 1/2 MA VA1 squared plus 1/2 MB VB1 squared. And you can do the same thing for kinetic energy after. Total kinetic energy after the collision. Just replace ones with twos. So 1/2 MA VA2 squared plus 1/2 MB VB2 squared. Now, if these two are equal to each other, we call this an elastic collision. So one elastic collision, that's when these two are the same. In other words, the change in the total kinetic energy, the total kinetic energy is 0. A very ideal case. I mean, billiard balls are close to it, but in real life, you never really conserve the total kinetic energy, okay? Whenever a collision happens, just because you hear it, which requires energy transfer, right? The molecules, the sound is just nothing but molecular vibrations, and that requires energy. So just because you hear it, you know that some of the energy is lost, okay? A car crash happens. You hear it, there's heat produced, and there's deformation to the cars, right? The object changed shape, which requires energy. These are all, the changes in internal energy in a way. So kinetic energy in real life is almost never conserved, but for problems, practical problems, problems such as, billiard balls could be considered elastic. So the second group then, inelastic, which means this is not conserved. And if there is energy loss, this difference in kinetic energy total will be a negative number, okay? Before and after total kinetic energies are not the same. The final kinetic energy is less than the initial kinetic energy. And number 3 in this list is completely inelastic, also called perfectly, maybe, completely inelastic. So kinetic energy is not conserved, but two objects become one. They stick together, all right? That's what makes it a completely inelastic collision. Suppose you fire a bullet into a target. The bullet enters the target, it embeds itself into the target, and they fly together. So MA and MB become one mass, which is equal to MA plus MB. That's what a completely inelastic collision is. So we can write the conservation law, for instance, as MA VA1 plus MB VB1. This is the total momentum before the collision. After the collision, these two masses move together. They stick together. So it's just one big mass. And they share the same velocity after. Just call it, I don't know, V. Call it V. All right? So that's the momentum conservation for a completely inelastic collision. Now, 2 on this side, head-on versus glancing, and 3 on that side. So you may have combinations. You may have a head-on and elastic collision, head-on and inelastic, head-on and completely inelastic. Same thing for glancing. You may have a glancing, elastic, or glancing and completely inelastic, okay? 2 cars approaching a broken light, one traveling north, one traveling east. They collide and stick together, and then the wreck, starts sliding, that could be a completely inelastic collision, but in a glancing way, a 2-dimensional problem. So that's what we're going to do from now on. We're going to go through these combinations and see what we can do, how we can solve problems. But keep in mind, all of this requires momentum conservation, okay? Momentum conservation is a direct consequence of Newton's third and second laws. So they are universal, okay? There are no exceptions. Momentum will be conserved as long as we are completely ignoring external forces. In the presence of external forces, of course, momentum is not conserved, right? You're traveling, you're driving your car, you speed up, you slow down, it changes. But for collisions, billiard balls and things like this, those problems, no matter what type of collision it is, momentum will always be conserved. Kinetic energy, you have to look at it. All right. So let me stop right here. In the next video, I'm going to show you how to solve some problems and how to maybe simplify these equations a little bit.